Kirill and Josef was my PhD students, and actually most of the things that I will present here is the part of his thesis. Okay, so first we'll give introduction, then something about the heterogeneous elastic rods, problem formulation and main results. So I have chosen to speak about rods, but actually the similar things that I will speak for the rods can be applied to the thin plates. And yeah, so then I will recall what Stephen was introduced already about, and Kirill was mentioning Gatman transform and resonant problem. Then I will talk about estimates and asymptotic expansion, what Kirill already introduced. I will do it in a slightly different way. Resolvent asymptotics. I will not do that for the full elasticity problem in thin structures because it's complicated, but I will show how simply the method in computations that we introduced, and I will somehow say that it can be applied to thin structures in elasticity. And then I will talk about non-resolvent approximation, and then I will mention the key differences in the case of plates, because I will be mainly talking about the rods, but actually the same method can be applied to the plates. Okay, so so you have oscillatory.
There is no difference. So
yeah. Okay, I will try to speak loud, and everything will be fine. And if you don't hear me, please tell me. Also, please free to interrupt me. Please free to interrupt me with the questions. Okay, you have a small parameter epsilon, which would be the thickness of the rod, and also the period of the oscillations, period of changing the material properties. So the material properties will be stored in the coefficient matrix function. It will be a periodic function. So we'll talk about some periodic operators in the background, and we will not assume the generacy of the material in the sense that you will have pointwise coercivity. In general, in elasticity, we will have this pointwise coercivity only for symmetric matrices, but here I want to introduce first the general elliptic problems or scalar case where you have pointwise coercivity, right? So this C is still a vector, not a matrix. And then you have the associated elliptic operator. Kirill was already discussing this case. I will simply fastly go through it. So we are interested here in homogenization now. What happens as epsilon goes to 0? And then you have different methods how to reach them. Kirill was already mentioning, so I will just fastly go through it. So we have some periodic media. You are looking at resolvent equation in the scalar of RD. And so you can define what you call the homogeneous media. So in a way, what happens is that when you have the mixed material with different properties on a very fine scale, you obtain the new material, and its properties are not simply the average properties of all the constituents, but you really obtain the new material which has completely different properties, and somehow the non-triviality of this formula is telling you that this will indeed be something new material, not just averaging of the old constituents. And then you have the limit operator, you call it, so this is this operator, which is of the same type, it's still coercive, with the same constants and still bounded with the same constants. And then you have the limit resolvent equation. And so qualitatively resolved that Kirill was mentioning different methods. For example, he was demonstrating Murat-Akhtar method. Is what happens if you have a deep convergence of the right-hand side, then you get deep convergence in H1 of the solution. But the question is, of course, what can you say quantitatively, especially when you go to talk about resolvents. And so the results are given. So in the sense of operator wrong resolvents are given by Billman-Sussenan. Also by Zhiko Pastuchova, but I will mostly rely on the technique by Billman-Sussenan. So you have this kind of results, and this is the first result. Kirill already mentioned how to prove with asymptotic expansion. Billman-Sussenan used different approach. So the second result is, of course, if you are interested in the higher order estimates, for example, L2 to H1, as a standard happens in homogenization, you need to introduce the correctors, because if you are now interested to estimate the derivatives, you know that if your linear is heterogeneous, so the qualitative solution will look like this, but actually what will physically happen is that you will have fine oscillations. And then, of course, this is simply in L2, this is in L2 norm small, but in H1 norm, this is big. And thus, you need somehow this corrector will capture these additional local oscillations that happen, and thus you need to introduce this guy here. So epsilon means that it is small in epsilon small in L2 norm, but in H1 norm, it is big. And also, what is given in the method by in the works by Billman-Sussenan, they were able to capture something that is called non-standard corrector in homogenization, right? And this is given if you want to estimate L2 to L2 norm, but with epsilon squared. Then you have, in addition to this corrector that you introduce, you need to introduce something more. Here, one additional corrector, and this is something that is called non-standard corrector. Well, this corrector first is a classical corrector in homogenization. It is related to the formula that Kirill already gave. So you have to solve the cell problem, then you multiply the gradient with respect to this solution, and then you get this corrector. But this other corrector includes some other parts, also in somehow non-classical corrector. What will be especially interested in the thin structure is not only this kind of estimates, but usually when you derive the equations of plates and rods, you need to scale the time. The reason by scaling the time is that somehow already Julius Kaplunov mentioned something like that. You want to somehow capture the moving of the bending, something that we call bending waves. And somehow these bending waves, they propagate on a different time scale than in plane waves. I will try to explain that during the presentation. Actually, you will be interested in estimating something like this. So this theta may depend on epsilon. And somehow, of course, the final goal is not the final goal, but one of the goals of these estimates is also to study at some point the evolution equation, and this is connected. Studying this kind of resolved problems is connected in trying to obtain the estimates for the evolution when you scale the time differently, or simply in some interpretations coming from the French school, they don't mention scaling the time, they mention scaling the density, which is essentially the same, but I like more the interpretation when you keep the density fixed and you scale the time, right? So let me just say qualitative results for thin plates, evolutionary thin plates. There are not so many papers that I saw, but I say Raoul in 1985, they derived qualitative results for the thin plates where the density is scaled with epsilon squared, and also Tambachade for my PhD advisor, he derived the qualitative results on the finite domain for the thin rods. Also, you have to scale the density in order to get the model that you essentially want, the model that sees the propagation of the bending waves. Let's go to the heterogeneous rod and explain what is our domain. You have cross section omega h, and then you take a fixed domain, you scale it with h, and then you take a period epsilon. At the moment they are different, but we will take that epsilon is on the scale of the h or simply equal to h. And then you have the elastic properties of the heterogeneous material are given with the elasticity tensor C, which has the properties that I already mentioned, that is the uniformly positive, definite, only on symmetric matrices. This somehow comes as the consequence of the property of objectivity, because, you know, in elasticity, the energy does not feel rigid movements, but here you are dealing with linearized elasticity, and so linearization of the rigid movements is actually anti-symmetric. So it's actually something that we call infinitesimal rigid movements. So this is an anti-symmetric matrices, and thus the energy or the elasticity tensor should be zero on this kind of displacements. So this is this property that it is only coercive but not symmetric matrices. So it is the consequence of the physical property of objectivity, and this actually is something that makes the analysis of the thin structures difficult, right? This is the key point where the analysis of the thin structures in elasticity becomes non-trivial. Okay. We will assume the symmetries. Okay, we have the results under the symmetries and not under the symmetries. So we will assume certain symmetries of the domain and of the elasticity tensor to get simpler results, right? And then we will discuss what happens if these symmetries are violated. Sorry, so we will assume the central symmetry of the domain when we are referring to the symmetry to the symmetries of the domain, and somehow okay, this will be the picture of periodic heterogeneous rod. So then we look the elasticity operator, and what we are interested in the non-resolvent estimates, and epsilon goes to 0, h goes to 0, but we'll take that epsilon is on the level of h, simply take epsilon equals to h. So what you usually do is that you rescale the problem on the fixed domain. You can write these equations. You can write these equations without the symmetric part, because these guys anyhow 0 on symmetric matrices. And thus, whether you write them or not is the same, but this is simply to emphasize the fact that this tensor is coercive on symmetric matrices. So this is our resolvent equation. And then when you do the change of variables, so you move yourself from epsilon size domains to the 1, so this is the further 1, then the price you have to pay is that the gradients become the scale gradients. Okay, so this is simply the change of variable. So you do in x1, you do the change of variable. So this is the physical variable, and the change of variable you do is the following one. Okay. So let's go to something. So first I will say what are the results, and then I will try to explain how to get these results. But of course, these problems of thin structures are quite old, and people had some answers that somehow from some other points of view came, and what should be the limit model? So, and what is important here is that I want to recall something that is called Kirchhoff-Love ansatz. For the case of rods, so it is usually done for the case of plates, but for the case of rods, it looks like this. So this D is simply the torsion of the cross section. P is the torsion of the cross section. A is extension of the in the third direction. So in the third, A is the extension in the third direction, and B1 and B2. So B1 and B2 are the simply movements of the are the movements of the line of the row. So the extension A is in this direction. This is the torsion of the cross section. This is the torsion of the cross section. And this is somehow the additional extension that appears as a consequence of the additional extension that appears in this direction as a consequence of the movements in the x1, x2 direction. So this is called something that is called Kirchhoff-Lava ersatz. And somehow if you try to write now what is the energy of this guy, what you will see here is that these two guys, the first derivative of these guys will cancel because here you take only symmetric part of the gradient. So somehow the first derivatives of B1 and B2 will cancel together with this guy, and you will take only second derivatives of B1 and B2 in the limit energy. While these guys here will be their first derivative. So torsion and extension in the direction of the row will be in the first derivative, while these guys here that measure how you move this line in x1, x2 direction will be with the second derivative, and they will be on different scale. It's important. They will be on different scale. Then they will be on a different scale than the torsion and direction and the extension in x3, and the extension in x3 direction. So somehow the interpretation of this, so you have something very complicated. You need to have to interpret it somehow physically, and interpretation of this is much easier for the thin structure. So it's much easier for the thin structure to bend. It's much easier for this structure to bend than to expand in general, right? And so okay. Yeah. So also this guy here on the right-hand side is something that includes moments of the forces. I will now go further and explain this in detail. So this is simply something, the intuition, what you would expect as a limit operator. As you can see, you have epsilon here, but somehow if you say that, if you allow that P1 times epsilon converges to something, right? Epsilon B2 converges to something, B and BA converge to something, right? Then we'll remove this epsilon. But the important fact is that bending deformations are much larger than the stretching deformations. We will assume, okay, when we are referring to material symmetries, although our results are independent of these material symmetries, but are much more complex in when they are not satisfied. When we are referring to material symmetries, we will refer to these material symmetries. And somehow, if you have these kind of symmetries on the elasticity tensor, then you will be able to divide your problem into two simple problems. That is the bending subspace and the stretching subspace. In the bending subspace, you have somehow deformations that are even in x1 and x2 variable in the first two components, and all in the third components in x1 and x2 variable. In the stretching deformations, you have the deformations that are all in x1, x2 variables, and even in the third direction, even in the, and so we can show that these two subspaces are invariant subspaces for the elasticity operator when the symmetry properties are satisfied. When I say symmetry properties, I'm referring to the symmetry properties of the elasticity tensor and the symmetry properties of the domain. So, and then you can decompose your operator into these two operators, right? Or you can decompose your tensor into these two tensors, and under the assumption of material symmetries. So let's go a little bit to the somehow physical explanation. So what are the bending and stretching subspaces? So bending, so this is something that you can actually physically feel. So if you are doing something that is in the third direction, O, then this will cause for the rod to bend, right? If you are doing something like this on the cross section, this will cause the rod to the bend. The same effect, so moment of the force in the third direction will cause the same effect on the rod as the forces in the first and second direction. And this will cause bending deformation, but this will be satisfies only under the assumption of material symmetries, of course. Now the stretching forces are the ones that cause, so when you pull the rod in this direction, it will cause stretching, but the similar effect will be caused if you take, so in this direction, like this, you pull the rod, then it will cause torsion, and torsion is connected with the extension of the rod, right? So this is the physical interpretation of the invariant subspaces that appear in the elasticity tensor. Okay, so we introduced these limit operators. The first one is the bending operator, the second one is the stretching operator, and somehow the first one is the bending and the stretching, and when the material symmetries are not satisfied, then you will not be able to separate your problem into two simple problems, and your limit operator, which is not actually the limit operator, but it is an approximating operator because you have epsilon inside, will look like this. What you will also see that the right-hand side becomes not trivial because you have the moments of the forces. So the moments of the forces cause something. They cause the stretching deformation. They cause the torsion. And here you have also the derivative of the force in the third direction. And this is somehow what Kirill was asking Kaplunov. So how is it possible that you obtain the derivatives of the forces in the derivatives of the forces on the right-hand side? But it is possible, and now we will see the results, and still the operator norm estimates will be in some sense valid, even you are forced to introduce the derivatives of the force in the third direction. So now we will see what are the results. So what are the results? So we have firstly under general. So first result is under general when symmetry under general assumptions and symmetry conditions are not satisfied. So what you see here is here is a smoothing operator. Here is m epsilon rho. It is introduced here as a coupling between these guys. So here you have smoothing operator. Here you have resolvent or something. So here you have the transpose of this operator, the adjoint of this operator, right? And so these are the estimates that we obtain. So, and these are on the right-hand side, you have these are normal sum estimates. So on the right-hand side, you have the force in L2, but the key fact is that here you have the smoothing operator, right? And this is why it was possible that you have the derivatives of the forces on the right-hand side. Under the additional assumption of the material symmetries, you have something like this, but in that case, so this is something connected with elasticity. Maybe it's better to skip that. You need to additionally to allow that you can scale the forces, because when you are deriving the thin structures, you need additionally to scale the forces in the third direction in order to obtain the full model, right? Otherwise, you will not obtain the full model if you don't scale the forces. So, and we are able to obtain these kind of estimates. So this is valid under the material symmetries, and this is valid under the full generality. I just want to say that this A epsilon rho is not the limit operator. It is the approximating operator, right? Because you have something like this. So your operator includes epsilon parameter here. So your operator includes epsilon parameter here. And actually, when you would try to perform the limit, when you would try to obtain the limit for the different parameters of gamma, depending on gamma, you would obtain different limits. But somehow, the fact that you are interested in operator asymptotics, but not the limit operator, allows you to express these roles, these results in a simpler form. Because, and there are two interesting regimes actually that are happening. One regime is for gamma equals to 2, which we call bending regime. And the other regime is for gamma equals to 0, which is called membrane regime. Okay, so these are two regimes that we are interested, but actually we can derive this for any gamma. And it is connected with the fact that, as I already have mentioned, it is connected with the fact that when you derive the limit models, so when you derive the limit models in elasticity, you need to scale the time or density. Okay. And then you can obtain in a similar way as Dilman-Sussenadi. By adding the corrector, you can obtain L2 to H1 estimates. Also, you need to add the corrector. And in the case when you satisfy, when you have material symmetries, these correctors, you can separate your problems into the two problems. And also, you can obtain higher order L2 to L2 estimates by adding additional corrector. And I want to emphasize the following fact is that the bending deformations are more irregular than the stretching deformations. Here, when you obtain epsilon to gamma to the power 2, that is the best you can obtain, because somehow this process of homogenization is connected with the fact that you will neglect in this operator, in the epsilon operator, you will neglect the spectrum of order 1 over epsilon squared. And because you neglect the spectrum of order 1 over epsilon squared, which is a high frequency spectrum, you cannot expect to obtain better error than this in this process. But when we are talking about bending deformations, it is not enough so to add the first corrector you obtain in the asymptotic expansion, but you have to go further in the asymptotic expansion to come to this point. We didn't do that, but our method allows to do that. And somehow, as I said, understanding of these structures is actually understanding of the bending deformations and the irregularity that they bring into the problem. Okay? So what is the strategy? What is the time first? For time. Okay. So use Gaussian transform in order to decompose the operator into direct integral of operators with discrete spectrum defined on invariant infinitesimal subspaces. Provide the estimates on the eigenvalue of these operators by using specialized Cohen's inequality. Identify the limit operator and then provide the normal resolvent estimates by performing asymptotic analysis, keeping in mind the scaling of the spectrum, and combine the optimal estimates into one uniform normal resolvent estimate depending only on epsilon by using contour integration. So I will try to somehow now go through this strategy and explain the proof of the results that I mentioned previously, and then at the end, I'll simply say what are what are the differences when you analyze the plates, and I will also try to compare what are the difficulties or new phenomenology that appears when you analyze thin structures with respect to the case when you analyze the full 3D model that is the analysis that is given by Birman and Susuna. Okay, so about the Gelfand transform, I will go very fastly through this because it is already 2 times introduced by Steven and then used by Kirill. You decompose your problems into you make the block wave decomposition, and then you make the Gelfand transform, you decompose L2Rn into these subspaces parameterized by quasi-momentum. We will do only the Gelfand transform along the thickness, so we assume that our road is changing itself along its length. So we have only one direction that the oscillations of the road happens, but the oscillations of the material happens. So what we will do is actually scale Gelfand transform because our period becomes small, becomes sextant. And then when you do the scale Gelfand transform, these are somehow this is somehow what is the inverse Gelfand transform, and this is somehow how it is related, how it behaves with respect to derivatives. And then so you can introduce the scale Gelfand transform like this, and somehow closely connected to the Gelfand transform is a Floquet transform, where instead of obtaining periodic functions, you obtain on each fiber quasi-periodic functions. So you can easily come from one to the other. So what will be our smoothing operator? Our smoothing operator will simply be the one that comes out of cutting the frequencies, higher frequencies than 1 over 2 epsilon. So the way how we come to the smoothing operator is that you take the Gelfand transform, you integrate it over the unit cell, and then you take the inverse Gelfand transform, but it is actually the same thing as doing Fourier transform and then it's inverse, but cutting it at higher frequencies than 1 over 2 epsilon. So this is indeed the smoothing operator, sigma epsilon that appears in the final result. Our problem now becomes of this form after we do the Gelfand transform, where you have this appearance. This we already have seen in the previous lectures. You have this matrix X high that looks like this, right? So this is after you do the Gelfand transform. So now you have decomposed your problems for each quasi-momentum into the family of problems that are on the compact domain omega times y. Y is of period 1. And and now either you look this problem as the problem of each unit cell periodic functions, or you will simply write it after using the Floquet transform. You will simply write it as the problem on each unit cell as a quasi-periodic function. Then it becomes simpler. But we will somehow in our asymptotic analysis, we will use the Gelfand transform because you have a small parameter Okay, and then by using Gelfand transform, we can decompose our resolvent fiber-wise. And then what we want to obtain is that we want to analyze for each high, we want to analyze this and obtain the approximation to resolvent for that resolvent. Okay, now let's go to the path estimates and asymptotic expansion. First, let's try to see what is the limit deformation, how it looks like. And somehow somehow when you derive the limit deformation, one important thing in elasticity is the cone inequality. And then what cone inequality tells you is that, so it's kind of the rigidity inequality, that you can control the deformation in H1 norm up to the infinitesimal rigid movement with the symmetric gradient. So with the L2 norm of the symmetric gradient. And what we needed firstly to do is we derived this cone inequality for quasi-periodic functions because you will analyze your problems on each cell. And then if you have in addition, so this is the classical cone inequality, but if you impose in addition that your U is quasi-periodic, then you can derive something like this. And if you go further, you can actually see that that for a quasi-periodic function, something like this is satisfied. And actually, you can prove it. So you start with the cone inequality, you use the boundary conditions, and you can prove something like this. And actually, what you can see here is that you rigorously derive Kirchhoff-Lava ansatz for the rods. Because this is exactly the derivative of this guy here. So if you compare it to the something that I previously called Kirchhoff-Lava ansatz, or the Bernoulli-Navier ansatz, as some people call it. So where was it? This has exactly the same structure. So this is exactly the same, but restricted on these finite dimensional spaces. Okay, and then so after you subtract these finite dimensional subspace, you obtain that you can control the H1 norm of field deformation with a symmetric gradient. And so, what can you conclude out of these estimates? So once you analyze the Rayleigh quotients, on these finite dimensional spaces, so it's actually 4-dimensional, you can conclude that the spectrum of A high consists of 2 eigenvalues of order high to the power 4, 2 eigenvalues of order high to the power 2, and the rest of order 1. Under the additional symmetries, on material symmetry, the spectrum is this joint union of spectra on bend and stretch. Of course, Stephen was already mentioning these things. And the spectrum in bending space, so bending, as I told you, understanding thick structures is actually understanding bending deformations. And so the spectrum in bending contains 2 eigenvalues of order high to the power 4 and the rest of order 1. The spectrum of restricted on the stretching deformations consists of 2 eigenvalues of order high to the power 2 and the rest of order 1. And this is what makes the analysis of these problems different with respect to the bulk case. Because in the bulk case, and also in the approaches of Birman-Susslina, you always obtain that, so they do somehow their approach by introducing operator pencils and starting from the spectral gel, and then they assume at some point, so they are doing something on very abstract level, and then they assume at some point that the spectral gel is regular, but the consequence of regularity of the spectral gel is that all the eigenvalues are of order high to the power 2. So this is why you cannot apply, at least directly, the approach of Birman-Susslina in the analysis of thin structures. Okay, and then, and as I told you, so what you need now to approximate is somehow in these non-resolvent estimates, so this, they are of order 1, meaning if you rescale your operator with 1 over epsilon squared, so these other eigenvalues are of order 1 over epsilon squared, and somehow in the process of homogenization, is about that you somehow neglect this higher order spectrum. So what you are interested in for each quasi-moment to approximate these eigen subspaces that have that have eigenvalues of order high to the power 4 and high to the power 2. In the rest, you are not interested. And if you want to do the homogenization. So homogenization is about somehow neglecting these higher order spectrum, right? So, okay. So what was, now we come to the somehow to the method that I want to explain or try to explain. So the strategy for asymptotics, so by a priori estimates, so by using this cone inequality, for quasi-periodic functions, we obtain these a priori estimates. Now, in our a priori estimates, we obtain that you have two eigenvalues of order high to the power 4 and two eigenvalues of the order high to the power 2. Under the assumption of material symmetries, you can separate these two subspaces and you can analyze these two problems independently of each other. But when the material symmetries, and that includes also the symmetry of the domain, are not satisfied, you cannot separate these two problems. Okay, but let's now, for the simplicity, assume that the material symmetries are satisfied, and then you have two problems. So instead of analyzing the resolvent part of epsilon squared, A high, we use something that I call physical scaling. You scale with the order of the operator. So in the stretching space, you scale with high to the power 2, the operator, and in the bending place, you scale with high to the power 4, the operator. And then we try to do asymptotics with respect to the quasi-momentum high. The goal is to obtain the resolvent of the something that is limit operator, but also to obtain the error for each quasi-momentum high. So Kirill has already shown how to obtain this. So you do asymptotics, but this asymptotics is in high, and it happens after you scale your operator. So let's go now, and now I will not do the asymptotics for this problem because it is complex in computation. I will simply show how the method works on the scalar case. So this is in a way different, a little bit different asymptotics than the one that Kirill presented, but still it's asymptotics in high. So what happens in the scalar case? So you scale your operator. So imagine that there is no this wild situation where you have two eigenvalues of order high to the power 2 and two eigenvalues of order high to the power 4. So you scale your operators with high to the power 2. And then you do the expanded solution. And somehow the way you want to do the expansion is to obtain u0, which is of order 1, then u1 will be of order high, u2 will be of order high to the power 2. There is no now epsilon in the problem, but it's only this parameter high. And anything you measure in high, thus it is natural that you will obtain the error depending on the quasi-momentum high. Okay. So this is what you do. You simply plug in. So there are no ansatz at the moment. So Kirill introduced us ansatz. There are no ansatz at the moment. You simply plug in into the equation. Okay. And you obtain this. You can give it to computer to do that for you. Right? Yeah, you plug in. Plug in the sum. Plug in the sum. You decompose your solution. Right. The answer is the sum. There is no anything else. But this answer we often use in another field, right? So okay. So you plug in this into the equation. This is it. And then you imagine that u0 is of order high, that u0 is of order 1, u1 is of order high, and so on. But I'm not writing the polynomials in high. In general, they are not. I'm simply saying that they are of order high, high squared, and so on. Okay?
So this is it. So now I'm identifying the members that are of order 0, that are of order high, that are of order high square, and so on. Okay, so these orange ones are of order high square. These 0 are of order, these blue are of order 0, red are of order high, and so on. Okay, so what happens firstly is that you conclude is that okay, you have similar equation as here, but now you need the expansion of the moment, so you conclude that U0 is a constant. This is somehow expected if you understand the operator with the constant coefficient, somehow its eigenvalues after you do the Fourier transform or delta transform will be constant. Okay, now in the second case you obtain the equation for U1 under the assumption that you know U0. This is the equation. So this is also material there. In the first step, you obtain corrector under the assumption, the equation for the corrector under the assumption that you have U0. And then you start identifying U2. And this is the equation for U2. And then you see that actually you need to guarantee that the solution exists. And you know that the solution will exist because the kernel of the operator are constant. The solution will exist if the right-hand side is perpendicular to constant, or tested of constant is 0. Or tested of constant is 0. So, and then the condition that the right-hand side of the constant is 0, so the solvability condition for the second corrector gives you this. And then the solvability condition for the second corrector, you work on it, and you obtain something like this. Right, so it was in the same spirit as Kirill did when he was explaining the two-scale asymptotic experiment. So first we concluded that the limit deformations are independent of y. This was his conclusion. In our case, it means that they are constant. In the first case, then you express the corrector. Then you express the corrector depending on this this U0, and then you try to compute the second corrector, and then you obtain the solvability condition for the second corrector, gives you the equation for U0. And this is in the same spirit as Kirill was doing his okay. And yeah. And so this is the and then this CCOM is this CCOM is this CCOM is your approximate result. And now but in order to obtain the error and to identify further correctors, you need to go further in the asymptotic expansion. And this you cannot do. This you cannot do because you need to satisfy the solvability condition for the U3. And you cannot satisfy it because you have already used your solvability condition. And now the question is how to continue with this asymptotic expansion, because you cannot satisfy the solvability condition for U3. And so the trick is that you restart the procedure from the beginning, right? So, and what is that? Now you invent U01, U11, U21, and then you plug it into the, again into the equation, and then you obtain again that U01 is a constant. Then you obtain again how you can express U11 with respect to U01. But now, since you can plug in U11, you have additional U01. Since you can plug in U01, you obtain additional degree of freedom. And then if you put it on the right-hand side, you can obtain the solvability condition for U3. Okay. And this is how you do it. So, and then the second cycle will give you that U01 has to be, has this formula, and it is actually of order high. Okay, so somehow the procedure is strange. You started with U0, that is of order 0. You define U1, that depending on U0, but then you restart the procedure and you obtain U01 and U0, that is again of order high. But this enables you, this trick of restarting the procedure, enables you to do the complete asymptotics in high. So, and now let me just say that, okay, in a way it looks unusual. In a way it looks unusual that you have to restart the procedure, but I want to add something, that this U0, so in this way you have obtained the equation for U0, you have obtained the equation for U1, and these are exactly, U0 is exactly the solution of the homogenized equation. U1 is exactly the classical corrector that appears in the homogenization, but this additional U01 is this non-standard corrector that is also already perceived by Birman-Sussenat, but in this way you obtain it by this restarting procedure. So in a way, so yeah, okay. Okay, and then stretching case is actually easier to analyze because in the stretching case you have the order of the quasi-momentum high to the power 2. But bending case, in order to obtain, as I told you, in the bending case you will get error that is weaker than in the stretching case, and in order to obtain epsilon gamma, in order to obtain the error of order epsilon gamma plus 2, you need to go further in the expansion to do that and identify further correctors. Okay, so how do we do norm-resolvent approximation? So this time you obtain, so in this way you have obtained this kind of error estimates, and they are obtained depending on high. So we have scaled the operator with high to the power 2, and we obtain the error depending on high. So how to obtain, but you are interested in obtaining the error, so the goal was to obtain the error from the operator 1 over epsilon gamma A epsilon plus I to the -1, and actually when you look it's fiber-wise, you are actually interested in obtaining the error in this guy, and then to take maximum overall quasi-momentum. This is what you are interested in. This will give you the final error. So how to obtain out of this error that is now scaled naturally, right? You have the operator that is scaled naturally because it is scaled with respect to its lowest eigenvalue. How to obtain the error for this operator? So what happens is that this operator, 1 over chi square A high, has two eigenvalues of order 1, but all other eigenvalues are of order 1 over chi square. And if chi is small, if chi is smaller than some constants, this will be far away from these two eigenvalues, and then you will be able to take the curve that captures only two lowest eigenvalues that are of order 1, and then you use this function in order to make out of this operator. You may use this function in order to obtain out of this resolvent this resolvent. So this is the trick. This is also somehow why the analysis of this guy was useful, because this guy has two eigenvalues of order 1, and all the others go far away from them when the quasi-momentum chi is close to the origin, which are the only ones that you are interested in if you are not interested in high spectrum.
in high oscillating, in high frequency spectrum. Right. So you use this function, and then you can do this estimate, and then simply by applying Cauchy-Integral formula or this representation formula, however you call it. Something with the block, but nothing works. Doesn't work. Okay, so this is what I already explained, and so so this is how you get it, right? Using Cauchy-Integral formula, and then you have the estimate. You can the estimate of this guy here. This is what you computed, and you can the estimate of this guy here, and this is how you can then obtain the estimate of this guy here. Okay, and actually, now just to say, so this was just the scalar showcase. So you have all the eigenvalues of high to the power 2. But actually, the case where you have two eigenvalues of high to the power 2 and two eigenvalues of the high to the power 4, in a way, is more complicated, but in a way, it's also simpler. Because with this method, I mean, because if you have you can look two operators, A high and this one, A high. So if they would be all of order high to the power 4, then you would have 4. If they would be all of order high to the power 2, you would have 4 eigenvalues in this curve, which you don't know whether you can separate or not, and all others are away. But now you have two eigenvalues of high to the power 2 and two eigenvalues of high to the power 4. And you analyze two different scalings for the operators. One scaling is this, one scaling is this. And then when you analyze this scaling, so what will happen? You will have two eigenvalues of order 1. You will have two eigenvalues of order high to the power 2, which will be away from this curve. You can choose a curve, and then all of the others will be of order 1 high to the power 2. So you will be able to separate these two eigenvalues by a curve. And in the same way, if you are analyzing this operator, then these two, lambda 3, lambda 4, which are of order high to the power 4, will be in one curve, and you will be able to separate them. Because this now lambda 1 is of order, since it was originally of the order high to the power 2, once you divide it by high to the power 4, they are of this order, and then all the others are of order 1 over high to the power 4, which for small chi goes far away from here. And then, so what you need to do, so what we do actually is that we separately do asymptotics for this guy here and separate the asymptotics for this guy here, do the estimates, and in that way you are able to obtain the estimates for the result. Okay. So in a way, and also, I mean, in a way, it's actually simpler. So something that from the abstract point of view, where you have spectral germ that you cannot reach because you don't have the regularity of spectral germ, is actually simpler because you have divided your problems into two problems. But the difficulty is, of course, that you have to do additional job. Besides analyzing the asymptotic for this guy, you have to analyze the asymptotic for this guy. So this is the idea. And yeah. And now, what can you do with these non-resolved estimates? Well, then, of course, as Stephen was mentioning, when you have a periodic operator, then curves will appear in the spectrum.
But in the limit operator, you have the operator with the constant coefficient, so the spectrum is all positive real line. So in a way, with these estimates, you can directly estimate the size of the gaps in the epsilon operator, because the limit operator does not have gaps. Okay, and you can estimate naturally because you obtain the resolvent for this guy. This is the resolvent you obtain. You can make them. You see, because if you only analyze the resolvent of this guy, then you will be able to estimate the gap. You'll be able to estimate the gaps of the interval 0 and nothing more than that, or fixed end. But here somehow you can do sharper estimates because you somehow were analyzing this operator. Of course, our motivation was not to obtain this kind of estimates for spectral gaps. Our motivation was time dynamics while we did these estimates. Depending on parameter gap, but this is some simple consequence of the fact that we analyzed this. Yeah, I will not now go to the case of plates, but just to say what is the difference, because I'm already out of the time. I will just say what is the difference. You have a different Kirchhoff-Love ansatz for plates. You have different chord inequality. These basic functions. So this is something that is maybe more familiar to people because people analyze more plates than rods in general. So you have different Kirchhoff-Love ansatz, but in the case of plates are a bit simpler than rods because you have one eigenvalue of order high to the power 4 and two eigenvalues of order high to the power 2. Yeah. And yeah, this is all. Thank you.